Here's problem 11. We got a car racing around a track 300 meters. At the instant when the car's velocity is pointed east, so I would draw that in, help me out. So there's my velocity. Its acceleration is due south. So acceleration is pointing due south and has a magnitude of 3 meters per second squared from above. Which way is the car moving? Well, this is the only information I have, so I'm going to look at acceleration centripetal equals v squared over r. That's the only equation I have that relates these. Right. Well, I know acceleration, I know radius, so I should be able to solve velocity just fine. Acceleration, we can see right here. So that's 3 equals velocity, that's what I'm looking for, divided by the radius, which is 300. So v squared will equal 900, so the square root of 900 is 30 meters per second. So automatically can't be any of these. So now, is it going clockwise or counterclockwise is essentially my choice. I have to figure out. Well, if I look at it, by drawing the diagram, I can see it's going to the east, so I can see it's going this way. So it will continue going that way, but just turning because of the force, so that direction is clockwise. Here on problem 12, we says we have a wooden block moving in speed v and a bullet's fired at it. How fast would the bullet need to travel? Anytime you have a collision, I like to use essentially momentum or change in momentum. And especially I can see my answers have m and v in them, and we know momentum equals m times v. So we got a couple different ways to solve it. You can start with the change in momentum of 1 we'll call this 1. Sorry about that. The change in momentum of 1, which we'll say this is 1, and this is 2, have to be equal and opposite because there are no external forces here. Okay. Now, why are there no external forces? Because I have the force of 1 on 2 and 2 on 1. Those are equal and opposite, so momentum will be conserved. Now you can do a lot of work working through that to get to how this problem works, but I'll give you another method that we saw by manipulating this around. You can also come up with, if momentum is conserved, that momentum total initial equals momentum total final. So that only works, again, if the net force is 0. So how I can do this is how many objects do I have before the collision? Well, I have objects 1 and 2. So I need the momentum of object 1, which would be m1 v1, plus the momentum of object 2, which would be m2 v2, right, equals, afterwards it says they stick together and the bullet's in there and it stops. Okay, so if it stops, there's both of them, so they're, and that could be just one thing, so this would be mass total, velocity total, but it stops, so this whole side becomes 0 afterwards. Okay, now I think I can change back to the variables. M1 we said was this little mass, so this is little mass times velocity of little, it looks like they're going with, okay, or that's the velocity we're looking for, so let's just leave it as v, plus here we would do m2, which is big M times big V. Okay. Now that V is going to the left, so it would be negative. So then what I could do, I have mv minus big M V because it's minus. So I could add it to the other side. So this side has mv. Then I've added this term to the other side, so that's big M V. We said little m V equals big M. Goodness. Equals, one more time, big M V. So I'm solving for the velocity on the left side of the equation, so I divide by little m, and that cancels. So that is this answer choice. Again, you could have gotten the exact same thing working through here. That's good for maybe conceptual problems. I like this one for conservation. Again, this only works if fnet equals equals 0. And on the system, so that it's on both of them in the collision.